Okay, guys, I'm going to give this a try. My voice is somewhat shot, but we'll go with it. So this is chapter 2, which basically covers scientific method and a little bit about matter and energy. Okay, so the first thing we've got to talk about is what is science. So science is kind of both a noun and a verb. It's something you do, but it's also something we know. It's the body of knowledge that we have about the natural world. So we're trying to kind of understand how things work in the natural world, and then we put it together in this collection of information about what we have learned. So science begins with observations. In fact, I've heard observation referred to as being the heart of science. Without observation, we have no body of knowledge about the natural world. We do have to make some assumptions when studying the natural world. We assume that it follows patterns and that these patterns are the same throughout the universe. We take these observations that we make and these data that we collect, and we assume that it can be applied to everything in nature that is similar. And the trick with science is we can't really ever prove anything. Things can be disproven, but they can't be proven. They can be well supported with lots of data, but never proven. So we do all of this using the process that you guys are familiar with, the scientific method, which doesn't have a set number of steps or even a specific set of steps, but it's a general process that goes something like what you see here on the screen. A scientist makes an observation that causes them to ask a question, and so they try to answer that question by doing some research, do experiments, collect data, and then based on all of that, they come up with a possible explanation, a hypothesis about whatever that observation was that answers that question. And then further testing is done to try and support or refute the hypothesis. So if the hypothesis is supported, then the experiments may be repeated, they may be tweaked slightly, or a different type of experiment that does the same thing can be performed. And if it continues to be supported, if the data continues to support the hypothesis, then it can become a scientific theory. However, if the data does not support the hypothesis, then scientists will go back and potentially look at other things and maybe revise the hypothesis and go through the whole process again. So I want to talk real quick about the difference between a scientific theory and a scientific law. So scientific theories are things that have been observed and tested and experimented on, and the data has supported them over and over and over and over again. And so it becomes a scientific theory. So it's not just a theory. Theories are actually very well supported with lots of data. It's not just somebody's random idea. There has to be stuff to back it up. And then scientific law typically refers to things that we have observed directly over and over again, and it's accepted that that observation is true across nature all the time. So the law of gravity, for example, we know that if you are holding an object up in the air and you let go of it, it's going to fall to the ground, unless it has helium in it and it's a balloon. But you know what I'm saying. The law of gravity we know is true. So one last little bit related to the scientific method, and that's the type of reasoning that is used when performing the scientific method. So we use inductive reasoning and deductive reasoning. So inductive reasoning uses specific observations and measurements to arrive at your conclusion or hypothesis. So you see it, you physically observe it. So the idea that all objects fall to the Earth's surface when dropped. You've seen that everything that you drop falls to Earth's surface. Deductive reasoning is going to kind of make connections between things based on relatedness. So we say something like all birds have feathers. eagles are birds, therefore eagles have feathers. So that would be deductive reasoning. And actually, there's a couple more things I wanted to talk about before we move on. Frontier science is something that is kind of on the front end of kind of the scientific process. It hasn't yet been well tested or supported. Doesn't mean it's wrong. It doesn't mean it's not eventually going to be well tested and well supported. It just means that it's in the early stages of that process. So we call it frontier science because it's kind of like when the early settlers were moving into the frontier. Sound science, on the other hand, is something that has been widely supported, tested, and accepted, and therefore it is something solid and believed in widely. So frontier science may become sound science, but it currently is in that early stage. Now, junk science is just flat out stuff that's kind of kooky. It's made to sound true and scientific, but it in fact is not. Another thing that scientists will sometimes do is create models. These models can be physical models, they can be computer models, they can be mathematical models, but they're basically ways of taking real life situations and making them simplified in a way of being able to even sometimes manipulate variables to see what would happen in the real world without actually having to do it in the real world. And this is particularly useful in environmental science because sometimes, we don't want to do something that would harm the environment, and so we will test it first using models before trying it out in the real world. Our next topic is feedback loops, and this is something that will come up again throughout the year because we talk about different environmental feedback loops at various points throughout the year. So first up is positive feedback loops, and this is when a system changes further in the same direction. Most of the time we're going to say that whatever the change is causing it to increase, and that increase causes it to continue to increase. So our example here on the screen is related to climate change. And if you see temperature, when the temperature increases, that causes permafrost in the tundra to thaw. And when the permafrost thaws, that releases carbon dioxide and methane into the atmosphere. Well, carbon dioxide and methane are both greenhouse gases that cause more heat to be trapped on Earth, which causes the temperature to go up some more, which causes more permafrost to thaw, which causes the release of more carbon dioxide and methane, and so on. So it creates this loop where the one component causes the next to increase, which causes the next one to increase, and so on, and it creates this cycle of increasing. Negative feedback loops, on the other hand, cause the change to be in the opposite direction, or it'll shut it off. One of the classic examples is simply a thermostat. If you set your thermostat at 72 degrees, if it goes above 72 degrees, then your air conditioner kicks on. And then when it hits 72, or actually goes just slightly below 72, the AC cuts off. And so it goes in the opposite direction. But in terms of a biological example, if we look at maintaining your glucose level, you've got a negative feedback loop system that takes place. So if your blood sugar goes up because you ate lunch, your pancreas will release insulin into your blood. The insulin causes your cells to take up the glucose and store them as glycogen in your liver. And when that happens, then there's less sugar in your blood. Well, then your blood glucose level declines and goes below a set point, and now you need some of that sugar. So your pancreas is stimulated to release glucagon. The glucagon goes to your liver and releases the glycogen, breaks it down, and releases the glucose into your bloodstream, and that causes your blood glucose level to go back up. So it's this constant cycling of your storing and releasing of the glucose to keep the blood glucose level at the right point. And so that's a negative feedback loop. Next, we're going to talk very briefly about matter. This is something you guys have had over and over and over again. So matter is anything that has mass and takes up space. It is made up of atoms. Atoms have subatomic particles, protons, which have a positive charge, neutrons, which are neutral, and electrons, which have a negative charge. The protons and neutrons are found in the nucleus of the atom, and the electrons are in the electron cloud. The atomic number is the number of protons in the atom. The mass number is the protons plus the neutrons. So in our example here of carbon, the carbon atomic number is 6 because it has 6 protons, but its mass number is 12 because 6 plus 6 is 12. However, you can have isotopes of carbon, and isotopes have a different number of neutrons. So carbon-14, which is one we talk about some because of its use in radioactive dating, has 8 neutrons instead of 6. So that makes it an isotope. Ions, on the other hand, are atoms that have gained or lost electrons and therefore have a charge, either a positive or a negative charge, depending on whether they have gained or lost the electrons. One of the ways that we look at and talk about ions is in relation to pH. pH is a measure of the concentration of hydrogen ions in a solution, and we can use that concentration to define a solution as being neutral, acidic, or basic. One that is neutral has an equal number of hydrogen and hydroxide ions and has a pH, therefore, of 7. A substance that is acidic will have a high concentration of hydrogen ions and has a low pH, so less than 7. Basic solutions or substances have a lower concentration of hydrogen ions and therefore have a high pH, so greater than 7. And the farther you go from 7, the stronger it gets. So the closer to 0, the more acidic something is, and the closer to 14, the more basic something is.